Let us start our 16th lecture, and in the 16th lecture we will continue on heterogeneous nucleation, and in the 15th lecture the way we have moved is basically we tried to see what happens if solid forms on a mold wall, and that time we have seen that it is forming a spherical cup and it is solid, and then we tried to find out what would be the expression for free energy change, and expression will depend on volume free energy change as well as the surface free energy change, and in case of surface free energy change, though there are two positive terms, but there is also a negative term, and finally, we will got to this particular expression. And then we started calculating what would be the volume of this particular curve. So, that means that volume is nothing but the V s, and we missed one negative sign here. You just have to put negative sign here, because when we had taken this, this particular thing was coming negative. So, that negative term will come here, and finally, the expression of V s would be, if we do that, V s would be like this. Now, similarly, we can also calculate the area of the sphere spherical part, this area we can calculate, and that area calculation again it will be a small integration, and that time if we remove this, so that time it is basically so this perimeter multiplied by this particular curved length, that become my A S L, okay, and the limit would be same from this to this, the 0 to theta. Okay. And now, if we do this particular treatment, so we do not have to do this particular adjustment. So, we simply directly we can get to minus 2 pi r square, because these are and this are, it will be cos phi and 0 to theta, and then it becomes 2 pi r square. So, this phi equal to 0 equal to 1. So, then 1 minus cos theta, I can make it 4 and then divided by 2. Yes. So, you will get this. Now, similarly, I have to also calculate, because there is a ASM term. Now, I can get to know this particular radius, this is capital R. So, capital R is nothing but, and if this is my R and this is my theta, the capital R is R equal to R sin theta. Okay. So, this is my radius. Now, the area would be simply that area. So, that means A S M would be pi r square sin square theta. So, it is simply pi r square. Now, we can also convert it in terms of cos square theta. So, now we have, and then we have also calculated this is A S L, and then V S equal to 4 by 3 pi r cube 2 minus 3 cos theta plus cos q theta by 4. So, if we simply replace these values here, okay, you just replace that value, you will get to an expression which will be, see if I try to do it here. I am not going into the details of this replacement and doing adjustments. You will get V del V del G r would be equal to minus 4 by 3 pi r q delta G V plus 4 pi r square gamma S L, this into, there will be one more term which will be 2 minus 3 cos theta plus cos q theta divided by 4. So, this part multiplied by this. See, if I take this thing, if I remove this part, if I remove the top part, so this is delta G r equal to minus 4 by 3 power I q and where S theta equal to by 4. Now, interestingly, since this is forming on top of a mold wall, let us put a name, let us give a name as het. So, this het is coming heterogeneous from heterogeneous. So, now in the beginning we have seen that when we first started attacking this nucleation process in solid liquid, delta G r homogeneous, this homo is basically homogeneous, was simply gamma S L. Now, you can clearly see that S theta. So, if we want to see the free energy change due to the formation of solid, which is not forming in the bulk, rather forming on the mold wall, we are having an expression which is a similar expression like that, but only difference is S theta, and this S theta factor is this. And in fact, during heterogeneous nucleation, this S theta is the factor which is extremely important factor, which decides how easily that particular mold wall will affect nucleation or will enhance nucleation. Now, in order to do that, we just try to plot the del G, del H r, del G r heterogeneous and del G r homogeneous on the same plot, okay, the way we have done last time. Now, if we have this expression, now at a particular contact angle, okay, so now we can also see what would be the unstable criticality. So, that means here also we will have a hump like this, and now this is the slope, and this would be my delta G r, and then its slope at slope delta G r dr equal to 0. Okay. See, if we want to try, if you want to find out what would be the r value at which these particular thing would go to 0, we can also do that, since s theta is independent of r. Okay. So, we will see that in this case, if we see would be equal to 0, and then we would get r star would be equal to similar like 2 gamma S L divided by delta G V. And if I reintroduce this particular thing into this particular expression, okay, you will see that delta G star hat would be equal to 16 pi 3 gamma S L cube by delta G V S theta into S theta. The critical R would be same at a particular temperature below T m, but delta G star heterogeneous, which is the activation barrier for nucleation in a nucleation formation, the stable nucleation formation, that is influenced by S theta. So, now if I try to see this delta G star hat equal to, this is the same as in our last analysis we have seen that this becomes my activation barrier for nucleation in case of situation, in case where the solid is forming in the bulk liquid and where it is not forming on any surface, rather the only interface that is there, it is solid liquid interface. That time this is my activation energy into S theta. Now, we let us see what does S theta do there. Okay. If I try to plot a function of r, last time we have plotted delta G r for homogeneous, it is like this, and this was my r star, and this is my delta G homo. So, I do not do it as delta G homo, so it is only delta G r. Now, this is my delta G r homo. Now, if I try to see the variation of delta G r heterogeneous, so that means this one, we have to see what is the value of S theta. Now, you will see that if we see this theta, which is the contact angle, if theta is small, then this term would be very, very small, because if we put theta value, you just randomly put some theta value. If we see theta equal to 10 degree, you will see that S theta would be around 10 to the power minus 4. Let me check the value. If theta equal to 30 degree, S theta would be equal to 0.02, and theta equal to 90 degree, S theta would be equal to 0.5. Now, it is interesting. That means, if I consider this expression, that means delta G r hat, this expression. So, that means, if the contact angle is 10 degree, that means theta is 10 degree, then delta G r heterogeneous at the same critical R would be very, very low, because as we have seen that R star does not change. R star in case of homogeneous or in case of heterogeneous, in both the cases R star remains the same, but The only difference would come in case of delta G are heterogeneous. So, there that means it is very clear that delta G heterogeneous at all the r, since theta is now 10 degree, would be very, very low. So, the peak would appear on the same r, because at the same time delta G star heterogeneous is also equal to delta G star homogeneous into S theta. Here also that similar reduction effect would come. You will see that this particular plot would be like this. So, this is my delta G R hat. So, now R star appears on the same line, even this point would appear on the same line, same point. Now, you see interesting thing. So, that means my activation barrier. So, if this is my activation barrier for homogeneous nucleation, at the same R, my activation barrier for heterogeneous nucleation would be very, very low. Now, if I try to find out what could be my nucleation rate, then at that particular temperature, this is at a particular temperature Tm. So, that time I can express that I in the form of similar expression, which is I0 exponential minus delta G star plus delta G d k T. So, their only thing would be in case of homogeneous it would be delta G star homo, and in case of heterogeneous it will be delta G star heterogeneous. But this term will not change, because liquid atom has to jump and come to the surface of the solid surface. In case of homogeneous, the liquid atom was also travelling through the liquid. In case of heterogeneous, it is also travelling through the liquid. So, this term would remain same, we can assume that this term remains same. So, that means, if this term reduces, what happens to I? This is an exponential factor, this is a minus term. So, the I would increase. Okay. So, that means that the same R star value, in case of heterogeneous nucleation, I would experience more number of nucleation per unit volume per unit time. So, that means, if I have a surface where contact area is very, very small, it gives me a very good influence for the enhancement of nucleation rate. That means, I would have easy nucleation. Okay. So, now what does this easy nucleation means? The easy nucleation means, that means I will not be needing much of energy for the transformation of solid from liquid. Okay. So, now when this surface would become very activated surface, okay. Activated surface means it will help heterogeneous nucleation. So, that means if I try to see the effect of this surface, we can have a plot where S theta can be plotted as a function of theta. You will see that the plot would be like this, and this is 1, and that time this would be 180 degree. And if I try to see what is the shape at these 2 points, the shape would be, in this case, shape would be like this, in this case, shape would be like this. So, that means, here the contact angle is very large and here the contact angle is very small. And in at 180 degree, interesting thing happens is basically is this. Now, this has been observed in nature. For example, lotus leaf. You might have seen a lotus leaf. If you put a water droplet, it forms a small sphere, and that sphere does not wet the surface, it remains as a sphere. So, that there I have a very, very large contact angle, and it does not wet the surface. And the lotus leaf, you just tilt it that water droplet will fall off and your surface would be absolutely dry, no water. Okay. So, that means it has non-wetting nature, and that non-wetting surface we also call it as hydrophobic surface. This hydrophobic surface is a very interesting surface where water does not stick. Now, on the other hand, that means if water does not stick, so that means I do not have any influence from the surface. If you see this particular thing, so that means if we do this particular thing, S theta becomes 1 when theta equal to 180 degree, and that time del G R heterogeneous equal to del G R homogeneous. Similarly, if S theta equal to 1, then delta G star heterogeneous equal to delta G star homogeneous. So, that means everything becomes very difficult for the nucleation, because it has to cross higher energy barrier. Now, in case of this situation where the contact angle is small, that means the surface, we say that once we put any, for example, is a water surface and is a paper, if you take a rough paper, if we put water, we will see that the water is gradually trying to wet the surface. Initially it will form a water droplet, but gradually it will create, it will try to get absorbed in within the surface, and the water layer initially it will be like this, it will be like this, and then gradually it is spread. Okay. So, that particular factor we call it wetting. Okay. So, this wetting is very important. Whenever I have influence of heterogeneous nucleation from mold wall, the liquid must wet the surface as quick as possible. Okay. And whenever the liquid metal wets the surface, that time contact angle would become low, and if contact angle becomes low, S theta would be very low, and S theta very low means delta G heterogeneous would be also very low, and it will enhance the nucleation. Okay. So, that means whenever we have a surface, it has to have very high wettability, and when I can have very high wettability, if we try to see the expression whatever we have on this particular section, for example, we remove that particular expression, we can get it back, that expression. Okay. So, let us get that expression. So, if we see, if we recollect our expression, that expression was this expression. Now, we can do it like this. SL. Now, if it has to, if theta has to go down, then cos would be, if theta is low, then in order to that case, this has to be low. Okay. If this becomes low, then S theta, theta would be low, and S theta also would be low. Okay. So, that means the surface must have very low surface energy, that means the mold wall. The mold wall would have a very low surface energy. So, if the mold wall has a low surface energy, then it has a very good wettability too. Okay. Now, what is its application? Okay. Now, we are thinking from all sort of expression point of view. The application is inoculation. Now, you might have come across this particular word called inoculants, and in the casting process we many a times we add inoculants in the metal, okay, and those inoculants act as a nucleating site, and those inoculant, on those surface of the inoculant, the liquid wets that surface and the solid starts forming on that inoculant, and if you add many inoculants, and at every inoculant you will have a crystal or the solid formation, and that means you have a very large number of crystals or solids, and gradually this is used while making a very, very fine structure or the grains in case of metals during casting. Okay. So, this inoculation is decided by the wettability of that inoculant, and finally, it has to reduce this term or this term. Okay. So, this inoculation, there would be many factors. The one major factor is wettability, and also there are factors like low surface energy, as we have explained, and then also we have to have a very good, say, for example, surface roughness is one factor. If we have then the compositional variation, sometimes we add inoculants which has to react with the metal and to have a chemical bonding, and those information would be very critical, but we will not get into those information. But at least from these expressions, it is very clear that we do add inoculants to making very, very fine structures. Okay. So, let us stop here. Now, in our next lectures, we will go to the solid-solid transformation, and once we have learned this liquid-solid transformation, understanding solid-solid transformation would be very easy. Okay. And then finally, we will go to the alloy systems, because most of the engineering metals will be alloyed. Okay. So, that case, how to we quantify this delta GV, that would be an important aspects. Okay. So, let us stop here and we will continue in our next lecture. Thank you.